we assume the deformation to be elastic, it can be calculated.
Oh yes, if it is elastic.
Right.
If it is
and
elastic,
plastic, then on the plastic
yes.
Properties, you
Yeah.
can do that.
Yeah.
And then one can get a contact area if you wanted to do it.
Yeah.
You have to make certain assumptions on what the deformation load is, and you have to know the mechanical properties.
Yeah.
And obviously the tip radius, which you know very well.
Yeah. Yeah. But even the point for such kind of tips, the available information is not really accurate. So if you, when they give you the spring constant, you give it from 1 to 6 Newton per meter. So there's some techniques, of course, to there's a very famous paper from Dr. Bouchon where you can calculate it directly, but this is a point of issue. The calibration with such kind of measurements is extremely horrible. But at the end, it leads to a very interesting.
Because when I saw that, at first, maybe this is very naive, but I was hoping that we could go to more microscopic, like what would be the contact pressure that I would generate.
Yeah, I like this.
The contact, and then I can design my switch so that I can extend that.
Yes.
Yeah.
If there is 1 minute, I can show you one of the figures. I have one presented here, which might be an answer for this question.
While he's researching, we obviously have calculated contact pressure in AFM measurements, and the pressure is extremely high, on the order of hundreds of megapascals. And the reason is we're using very short tips. So regardless of the mechanical properties, contact area is very small, and the pressure is going to be on the order of 100 megapascals in typical silicon type contacts. So depending on the properties here, it could be very high tip. So we're dealing with very high pressures, although the loads are very small because of the short tip.
This is actually the friction studies which we have not shown. Where here, what we can find is, I don't know if it is clear or not, we can close this. Yes, here actually, what we have is, we apply a contact between the tip and the surface, okay? And then we measure the friction force and then the friction coefficient. But the issue here is this increase actually in the applied bias is increase of the normal load. Normal load actually is the contact force between the tip and the surface at different electrostatic force. So we can calculate this. Simply what you can do is you get this parameter called TM deflection set point, you have another parameter called sensitivity, and based on this you can calculate the exact normal load or contact force at a specific electrostatic field. So this might help. I don't know if it helps or not. We can calculate it based on this. Might be I did not answer the question correctly.
Because what would be nice is that
Yes.
you can come with your characterization method and you can tell if the design of the switch is going to be the same in the charge. But that's the
Yeah.
because you don't know exactly the surface.
Yes. The area also is important. This okay.
Okay, I have, when you do the testing on MIM capacitors and you just inject the charges through the MIM capacitors,
Yes.
you need the electric flow, right? You just
Which electrode?
the top electrode.
Yes. So yes.
Okay, so this is what you go.
Yes. This is a MEMS. This is a concept actually behind it. Yeah.
And the other thing is that you focus on, as Ingrid mentioned, you focus on contact points and a good, when the metal is in contact with the electric.
Yeah.
And the thing is that when you do a MEMS device, most of the electrode in the downstate is not in contact with the electrode.
Yes.
Yes. You mentioned
This air gap submission.
So this is going back to the question of Ingrid, is there a way we can correlate the, how to say, the restoring, the pull-out voltage that corresponds to how to the restoring force, the surface actually contact. Like we're doing you know, when we make onic switches,
Yes.
we can correlate the surface of the contact.
Yes.
Actually in contact with the contact resistance. And here can we extract it maybe from the downstate capacitance or something like that?
I think for MEMS switches it could be done, but this needs also, this might be done with the help of atomic force microscopy as well, because with atomic force microscopy what we can do easily is you have a topography image for the whole area, and this is done already by the way here in, by David with Patrick, where they have a full image of the topography, including actually these stuff. And then what they did is they take this nanoscale data and then they enter it to ANSYS physical modeling just to calculate, I guess it was the contact force between two surfaces, so including the real surface topography. So I think it could be done, but we need real data from real MEMS devices. But the question would be, even if you do this, are you sure this is reproducible for next device?
No.
This is a point.
You get some things statistical.
Yeah.
I expect that on the wafer or on the
But
this one is going to be more or less
yeah.
the same for all.
I believe AFM could help a lot with this.
The last point, I have too many things, so I will just stick with one. If we can go to the slide 30.
Yes, 30 or 30?
30. Yeah. Basically, your
Yeah.
conclusions are that a thick dielectric has a lower time constant, which is if you inject charges from the top, then it should take longer for them to cross and go back and be collected by the local electron.
Yes, actually we were thinking like this in the beginning of our work.
How do you explain that? I mean,
This is a good question.
missing.
Actually what we did in the beginning, in JMM data, what we have seen is we find actually what we were telling exactly. If you have a thicker dielectric, you have longer decay time constant. And we were believing that this is because of the probability of random walking particle, which is moving randomly till it reaches this one. So logically it was expected for 500 nanometer to take longer time to reach it. But the problem with these measurements we did in JMM is that it was at the same bias. This was actually what we did in JMM, in a different way. Then we said, okay, fine, we agree now, it is following this random walking probability. What about applying the same electric field? And when we did it, we find this. It is not this. So this mechanism actually was not right for this. I don't know really. I still, by the way, we have discussed this many times. There's two issues with the thickness. We have to understand first why, when we increase the thickness, we inject more charge in the same electric field. This is the key to understand then how your charge is collected. I believe if it is like this and the decay time constant is not dependent on the thickness, this means the random walking probability theory is not right for this. How come it is really collected in the same way with thicker and thinner? I really don't know. Might George have explanation for this? You know, we spend a lot of time with the thickness and we still were not able to understand why this happens. I would have been very happy to find a difference in this charging as well. I did not find. And we verified this with, and this is the way actually why we did DCT, then Kelvin force microscopy, then force distance. I was looking just for a small difference. I did not find. Sorry, I did not answer your question, but we really don't know.
This is honest and
We really don't know.
the last thing I have one last question is some groups like Raytheon, they work with very thin membranes, metal membranes,
Yeah.
and very thin dielectrics. And the point is that they want to have a very intimate contact of the upper membrane so that they have almost a perfect NIM capacity of the device in the downside, and they have very thin dielectrics so that when you shut down the voltage, all the charges are
Very fast discharging.
So how do you, from what you've seen, what do you think of this approach? Do you think it works? Well, compared to what is done here and in many labs where they have a very thick and strong beam that comes into contact and that does not connect very well.
Yeah.
What is your feeling? Should we expose to something that is very much
One thing which we should also consider about is the interfacially charging MEM capacity. What we have seen from here is that MEM and MEMS can lead to similar results, but there is a very important difference between MEM and MEMS also, which is the metal layer touching the electrode, which means you have another interfacially charging. I don't know how much this could affect. We have not seen this effect in our measurements. So with this structure, if we are going to use it, we need to be careful about this interfacial charging. It might be dangerous. It might lead to more charging actually. But I really don't know. But what about the restoring force? Because normally if you use a very thin,
It's computed to that working. It's actually it's more.
yeah, I don't know, but it's.
That's a question that.
Yeah, actually, this is a good point to mention. We have shown a comparison between KPFM, MEM, and MEMS, right? We have not compared with SEMFIL. You have seen this always. Because actually, the comparison is impossible. Why? Because in Kelvin force microscopy over MEM, you charge the whole area at the same time. In Kelvin force microscopy SEMFIL, you cannot do this. You inject only in a point.
Yeah, and so it's not to spread like.
Yes, this is one option. Yes, the other option is you scan an area with higher potentials. This is also possible. But if you scan an area, there's two problems. First, it is not, yes, simultaneous charging like MEM all the time. Fast means what? This is the point. Fast means we have to know carefully that it's charging time constant. This is one point. The second point is we have to have the same charging time for both Kelvin force microscopy SEMFIL and MEM. Why? Because we have shown clearly in one of the papers that increasing the charging time will lead to different injected discharge density and then longer charging time, longer relaxation time constant. In this case, you will never be able to compare. One of the solutions I was thinking before about is we can use Kelvin force microscopy SEMFIL, but instead of making it charging in a point, what we can do is we stick a ball, okay, this is done many times in the lab of Professor Bouchan, and then we coat it with metal, then we can come in contact or not. In this case, we can avoid interfacial charging. But actually, preparation of such tips with ball is not easy, and there was no time to do this. But it's an important point to be done. I think AFM also can help with this.
I have many questions because of the interest that was made by your thesis. And I want just to conclude and say that it was very, very nice and very, very happy to be here.
All right. Thank you very much. I appreciate it.
The last thing I wanted to mention is that the main point for our friends today is packaging and reliability.
Yes.
And we need to focus on these 2 points on the way to discovery.
When you say packaging, you mean the packaging cost or the topography or the time?
Find a way to package them
With no cost?
and then go on with what
Yeah.
the rest of the
Which one is-
applications will come anyway.
Which one is more critical? I'm sorry, I cannot ask a question. Maybe.
They combine.
I see. Sorry.
Think about you, multi-physics.
Multi-physics. Yes.
Combined
Which is
physics.
first? I see. Thank you.
So thank you very much. So I propose to continue by the minus from the far to the near report. So maybe Professor Bouchan, you can
All right.
continue.
I was introduced exactly 2 years ago. I came to give a talk in a conference organized by Patrick on MEMS. And at that time we talked about a collaboration, and we talked about if he had a student who'd like to come to my lab. Fortunately, I met Osama during the trip, and a couple of months later they decided to send him. And he's been in my lab a total of 3 trips. He spent about a year. But as you can see, for the quantity of the work is done would be equal to a normal student for several years. So he works extremely hard, he's dedicated, he's very independent, he's very original. He goes out and gets help. He doesn't seek, he seeks help himself. He's not looking for somebody to come and help him. Just to give you an idea how dedicated he is, first time he came to my lab in February last year, he brought his wife with him. She was pregnant. She delivered a baby, I think, in April in the morning, and I saw Osama in the afternoon in the lab working.
Well, actually, I went to my wife after the university. So.
And then I think I saw most of the time while she was in the hospital. I don't think he missed a beat. And I asked myself, who the heck would ever do that? And I thought of me. So Osama was looking for a genetic copy. I found one.
Thank you you very much.
So it's really, he's done a good job. And so he and I had lots of discussions when he was in the lab and we wrote the papers together. But I guess as a member of the committee, I'll ask you a couple of short questions.
Sure.
And the first question I'll ask you in ministers, that's my favorite thing, something I've been working since 1981. I used to work at IBM. And I've been floating the idea of ministers being important in MEMS switches. So go to slide number 18, I think it was. Yeah.
Or just before this.
Yeah, no, that's the one. That's the one. Go back to the one you just had. Yeah, I want to see the minister's cartoon. Okay. So here, what you're showing is schematically, you're showing an asperity on a bridge in this case, with a spherical shape coming in contact with the electrode underneath. Now, when I look at this menisci, they're concave shaped. Now, are they always concave shaped, or they could be convex shaped?
I think they also could be different than this.
Under what conditions? Why did you draw them as concave shaped?
Well, actually, this is, let me think about first well, it depends actually first on the contact shape we have. So in this case, we have a spherical contact. While it might not simulate really the real asperity with MEMS switches, it might be different. I think also it depends on the surface tension of the liquid layer we have. Might be different based on this.
Actually, it depends on contact angle. It depends on hydrophobicity of the surface. If the surface is hydrophilic, if both of the surfaces are hydrophilic, meaning if the contact angle is less than 90 degrees, it turns out they'll be concave shaped. And what concave shape does, the pressure inside the meniscus is negative, less than ambient. And that's what leads to an intrinsic attractive force. And if you were to plot this cartoon for surfaces which are hydrophobic, they'll be convex shaped. Actually, there'll be a positive pressure. What they're going to do, they're going to push the two surfaces apart. So you'll have negative adhesion. Okay? And if the surface is hydrophilic, then you're going to be pulling them.
Okay, I think this comes also from the definition of the contact angle itself, how it looks like, right?
Well, if just simple physics you can derive, that shape has to be concave shape.
I see.
Okay, so now at the bottom, you write an expression for the meniscus force. So when I look at that expression, the meniscus force is a function of radius of the asperity, surface tension, and the contact angle.
Yeah.
I don't see any influence of amount of liquid which is present in this equation.
Yeah.
So later on in your talk, you found that as you increase the relative humidity, the thickness of the water film goes up, which is what is responsible for increasing the meniscus force. I don't disagree with your conclusion, but what I'm asking you to explain it to me, based on this equation, how do you explain the meniscus force increases as you increase the film thickness?
Well, actually, the radius will be changing if we have different amount of liquids. And the contact angle also will be different. Right?
Contact angle is a property of a liquid solid interface, and the radius is of a solid surface. So they really should not change.
So the only remaining parameter actually is this.
And that should not change either.
That should not change, yeah.
That should not change either. So then why does it change? Okay. What it is this is a simplistic
I think
cartoon of a very single asperity contact. Although at the bottom, we claim there's a single asperity contact, but when you look at the tip of the tip of the tip, you have these nanoasperities. So what is really happening is you're making multi-menisci because of that. So what's really happening is as you're increasing the liquid, now we have more of this nano roughness which is present on the tip, creating the meniscus bridges.
Okay.
So within a single asperity contact, you have multiple asperity contact, and that's really what increases it.
Okay.
So another argument is that if you didn't have the two in contact, and then, so that equation has been written when the tip is in contact with the sample. When the tip is not in contact with the sample, the
Yeah,
liquid
protecting
film,
us first.
there is a different relationship,
Yeah.
and where explicitly H comes into the picture. Okay, H comes into the picture. So if you go back to that previous slide,
It was number 18, I guess.
18 I think it was. Okay, what you're shown here is the tip is in intimate contact with the surface underneath.
Yes,
So what you do is you lift the tip
I have
and
read
pinch.
this.
And you have the,
I read
so if you
this,
remember
I
in
read
my
this.
book, there are
Yes,
three
yes, I have read
regimes.
this. I read this. I
So it's
discussed
the
this.
other regime which explains it.
Yes, I remember this. This was the simplified model
Right.
for meniscus.
Simplest model.
And
They
it
use
is
it all
actually,
the time.
yes, and actually it was based also on the assumption that this is a spherical shape. If
Okay.
we change this a lot, I remember this
Right.
now.
So just to continue that,
Yeah.
so now what you do is, you put in vacuum. Okay? Wait, before you answer it. If you put in vacuum, you're still going to have some force, aren't you?
Yes, but there is no meniscus force here.
What force is it? When you bring two solids in contact, there is going to be force.
We have van der Waals forces.
Exactly. As a minimum.
Yes,
You always have that.
Yes. The point is we have these forces, but the point is, I cannot ask you questions, but this might be a question also. What is the vacuum level we're talking about? I think this is also important for the packaging of MEMS switches, because this might define which packaging, which vacuum level you need for a proper packaging to release in the sky. Okay.
Let's say the last part of the question regarding meniscus
Yeah.
is, so what you've seen, if the surface is hydrophilic, meaning the contact angle less than 90 degrees for a given liquid,
Yeah.
you form this concave shaped menisci, which results into the intrinsic negative pressure or intrinsic attractive force because of negative pressure. So what are sort of things you think one would do in general? Let's forget about a switch for a
Yes.
second,
Yes.
with something may not attractive. What sort of things would you do to get rid of it?
From what exactly? From the
Meniscus.
Actually,
I don't
there
want
is
to form that. I don't want to form a meniscus.
yeah,
in
yeah,
general.
there is many.
In general.
Yeah, there's many solutions for this. One of these solutions actually is to modify the surface structure actually using different techniques. One of these is to make this nanostructured stuff over it, where we can, like actually the Jacob effect, where you have these nanostructures, nano patterning.
Lotus effect.
Lotus effect.
Lotus
It is lotus. Yes.
Gecko is the opposite. Gecko increases adhesion,
Uh,
and lotus reduces adhesion.
it is.
So one of the approach would be
Lotus
the lotus
effect.
effect.
Sorry.
Which is just the reason I got into Lotus League, by the way,
Yeah.
8 years ago, to get rid of that.
Yes,
What
actually.
would be the other classical technique? So that's more recent. What would somebody would have thought of 10 years ago?
Yes, what we can think about is to develop anti-stiction layers actually, using
Exactly.
these sand layers, surface layers.
The simplest example we have now.
Yes, I like this so much actually. And by the way, actually, I put it at the end of my presentation.
I
When
saw
think
that.
about the, okay.
I saw that.
Yeah,
But I
anti-stiction.
just wanted to bring attention
Okay.
here. So you bring anti-stiction layer.
Yeah,
Right?
sure.
The simplest example would be a Teflon.
But the
Alright.
point here is for MEMS switches, we need also to investigate the effect of this sand layers on the charging. Yes, we developed sand for anti-stiction stuff, but not the
Exactly.
effect on the charging.
Exactly. But it may not be practical in switches, but nevertheless,
We,
there are ways of handling that situation.
yeah, there was actually a trial from here in DAS. There's a company called 31 Degree working with this surface monolayers for anti-stiction stuff for MEMS switches.
Okay.
I have some samples, but I have not the time to investigate that.
So-
We did it in Eindhoven microgroups
Yes?
to look at stiction due to
Okay.
It helps to the users.
So
Yeah.
it was anti-stiction layers also? Or?
Some
Okay.
By the way, the people in MEMS community here, a lot of this work started from hard disk industry. So I've been in this business since 1981. And actually when nanotechnology industry came in the 90s, they sort of read the literature and they adapted that. But the hard disk industry suffered through the stiction since 1981. Actually the word stiction was coined in IBM in San Jose where I used to be. Because the drive got stuck because of high friction, came the word static friction or stiction. So that's what came over. So I don't need to...
I just remembered one more thing we can add actually to avoid this, which is using this stuff I have attended for the hard disk, where they were making some sort of induced roughness actually to avoid this contact
Well,
contact area, and this might help
To
also.
minimize large menisci.
Yeah,
is what it is.
yeah.
So I just ask you one more general question, and then I'm going to pass it on to the next person. You talked about lots of different things. Obviously, I'm a fan of your work. I mean, you're an ideal student. I'd like to have another copy of you if I can find one.
Thank you.
Maybe I'll go to somebody and create a genetic copy. You have developed novel measurement techniques. You have provided detailed understanding of charging phenomena, and you provide a general understanding and introduce the meniscus and the electrostatic switches. So the general question I'd like to ask, and I normally ask in the US and every PhD defense, is what you think is a seminal contribution, a single seminal contribution you have made in your thesis, which has scientific implications, and as well as could change the way we design switches, or may improve the life of Professor Blondie in as he tried to develop it. So what do you think your single most
I
contribution?
have it in mind actually.
All right.
Developing the force, distance, curve methodology for studying the charging. And what results mainly from this, which is electric field induced meniscus.
Okay.
This is, I do believe it is really the main contribution which could help to develop these devices.
So based on this work, if you were to design an improved switch, how would it be different?
Many things will be changing.
No,
The
just
first
tell me one most important thing you will do which would be different, which would have a Sama stamp on it.
Actually, using this, you could change many things, but I think the most important issue here is packaging environment for MEMS. This is the key. I think this agrees also with what.
And that recognition comes because of the meniscus work.
Yes.
I mean, it doesn't come from the charge retention.
Yes, it actually
That's
comes from.
very clear scientifically, because when you look at the meniscus, you obviously know the environment plays a major role.
Yeah,
So that's crystal clear because of that.
The other issue is the multiphysics coupling between both phenomena actually is really very interesting. We should
Right.
be careful about it.
Thank you.
Okay. Usama, thanks. It was very nice presentation. The work is very impressive. Just one question. Can you go to slide, I think it's 31, I'm not sure.
18 also?
31, 31. The one where you show for the first time the full width half maximum, yes.
Okay.
No, it's,
This one.
okay.
No, but the first time for width it was for the thickness actually.
Go up.
I think it is here. It was an example of Kelvin force microscope, so it should be here. Yes. Is this one? Yes.
Okay. No, one distribution with real dimensions. I mean, just to show, to observe that one step down,
Goes here.
probably even more.
We can go for this
Okay.
one, if you
It's
like
fine.
this. Okay.
How really nanoscale can be this?
Well, why it is called nanoscale, you mean? Or
Yes,
because it's micron?
Yes. In nanoscale, yes, I would. Okay, it's fine. It's very good job. But how really nanoscale is this?
Yes.
And how do you think that you will really achieve to have a nanoscale measurement?
The main issue here is, if you look at the whole X range, it is 2 micron, right?
Less. I would say less than 1 micron. But okay.
This is 1 micron, this is 1 micron, so the whole is 1 micron, right? And if we look here, actually, we would find the real value of the full width at half maximum, which is actually in nanometer, fine? Which is less than 0.5 micron. The message here is, when we say nanoscale, we do not mention or mean I'm working with 1 nanometer spreading of the charge over the surface. Why? This could be done, by the way. I'm going to say how this could be done right now. When we say a single asperity, this is really not accurate because we don't know the dimension of a single asperity. This is one point. The tip shape we are using for this is SCM PIT tips, which has 25 nanometer as an apex. So when you inject a charge, actually, you should inject a charge in this area only. You can say maximum 50 nanometer. But when you measure with Kelvin per force microscopy, and this is a problem with force microscopy actually, you inject a charge in 50 nanometer, right? So I was expecting here something like 50 nanometer, but what we have here is also a factor of 10. Because you are not measuring this point only. You are measuring actually the surrounding area, which is based on a parameter called lift scan height, the separation between the tip and the surface. How come we say nanoscale and it is not real nanoscale? The idea here is to simulate the distribution of a charge, to understand the distribution of a charge from the contact area between a tip and the surface, considering a tip as a sphericity. This scale of 1 nanometer and 2 nanometer we still could do easily using very fine tip. Is there something like that? Yes, of course. There's many tips right now which is based on carbon nanotubes, where you can use it and then you inject a charge with it. And in this case, actually, I expect, I don't know, but I expect, based on a discussion with a colleague from a company developing these tips, we could have around, actually it was like 10 nanometers, so we could have, might be like 50 nanometer or so. So the message here is, yes, this is not really a nanoscale, but this could be done using other tips. The other important issue is that here, we don't measure exactly what we inject, we measure an average. And this is a very big limitation with Kelvin force microscopy, which is solved by FDC. You might ask, so why you injected the charge in points if it has all of these limitations? Because the issue here is, when you inject in point actually, suppose that the surface potential at this point exactly is like 20 volt. Kelvin force microscopy cannot measure this. And it will give you, might be like 10 volt only, because here it measures from this point, and the capacitance from this point and this point. If we go for area charging with like 50 volt, the induced surface potential will be like maybe 30 volt. Kelvin force microscopy will saturate, it will not measure this. And that's why we had to go for point charge. And this actually focuses also on the beauty of FDC techniques. I hope I answered the question. Thank you.
Okay, the next question
Yes.
is, what is really important in FDC on MIL? I understand FDC on MEMS, on the bare dielectric.
Okay.
But FDC on MIL, it means that we are going on the top of a metal surface.
Yes.
So what is really more important with KPFL except of the amplitude of the surface voltage? If you exclude the amplitude of the surface voltage,
Yeah.
what is the benefit of FDC on MIL? On MEMS, yes, because you have the bare dielectric, you charge the dielectric, but in an MIL capacitor, you're just looking on a metal.
But this metal actually is reflecting the electric. It is Kelvin force microscopy. MEM is almost the same like FDC MEM. The same strategy. We stress the MEM, then we measure.
The strategy is the same, but I mean, you have in a MEMS switch, you have the dielectric,
Yes.
and you charge a surface, you control surface,
Yes.
control area.
Yes.
On MIL, you are just dealing with a metal.
Yes.
So anywhere across the metal you go, you will find the same.
Yes. Actually,